Hello everyone, my name is James Pruitt and this is my fifth lecture on generating functions. I'm going to start off with a theorem um, and it's going to state if an and bn are sequences whose product whose product has a multiplicative inverse, then both the sequence A sub n and B sub n have multiplicative inverses. Okay. If let me read this real quick. If the sequence A sub n and B sub n are sequences whose product has a multiplicative inverse, and that should be then both the sequence A sub n and B sub n have multiplicative inverses. So we're going to let A be the generating function. Let me get my let in there. Let A be the generating function of A sub n, and B be the generating function be the generating function of Bn. Okay, from the hypothesis we know that the product AB has a multiplicative inverse. So by the hypothesis we know that AB has a multiplicative inverse, which means there's some sequence whose generating function we'll call C. There's some sequence such that the product of AB with C is equal to 1. That's what it means for AB to have a multiplicative inverse. And since we know that our sequences together with addition and multiplication is a commutative ring, we're going to apply associativity. So A times B times C is equal to 1. That's by associativity. So therefore A has a multiplicative inverse. So the sequence AN has a multiplicative inverse. Okay, and we're going to do the same thing. We're going to do commutativity, and then commutative ring. We can do commutativity. So B and then associativity. A times C is equal to 1, and so therefore Bn has a multiplicative inverse. And that's all we had to do for that proof. We're done. Okay. I'm going to prove another theorem here, and this will qualify, this will describe, so once I prove this theorem, we'll know everything there is to know about multiplicative inverses, or completely define multiplicative inverses, if that's a better way to say that. So if AN is a sequence whose constant term is 0, then then AN has that's ugly. That's not much better. Has no multiplicative inverse. Okay, so if the sequence AN, if AN is a sequence whose constant term is 0, then AN has no multiplicative inverse. Okay, so we got AN, and we know that A0 is equal to 0 by the hypothesis. So we're just going to let Cn, let Cn equal to our sequence of the hypothesis A sub n times an arbitrary sequence B sub n. So we know that C0 is equal to A0 times B0, which is equal to 0. So the multiplicative identity has a non-zero constant term equal to 1. Has a constant term equal to 1. So our constant term here of the product of anything that I multiply by AN is going to be 0. Excuse me. So AN has no multiplicative inverse. Okay. So that's proved that. So now we've completely described multiplicative inverses. If the sequence has a non-zero constant term, then it has a multiplicative inverse. If the sequence has 0 as its constant term, then it has no multiplicative inverse. Okay, so with that said, we're going to move on, and we talked about, we found multiplicative, we computed multiplicative inverses, or we guessed multiplicative inverses of this the sequence whose generating function is this. And we found that the generating function of the multiplicative inverse of that sequence to be 1 plus x squared plus x cubed plus ... And we also computed or guessed the generating function of the multiplicative inverse of the sequence whose generating function is this. And we found that that is 1 plus cx plus c squared x squared plus c cubed x cubed plus ... So now we're going to talk about notation, and this is a common fashion with dealing with rings is to use the fraction notation for multiplicative inverses. So it's common practice for arbitrary rings to use 1 over 1 minus x as the multiplicative to represent the multiplicative inverse of 1 minus x, and that's equal to 1 plus x plus x squared plus x cubed plus ... And also 1 over the multiplicative excuse me for a second. The inverse of the multiplicative inverse of 1 minus cx is equal to 1 plus cx plus c squared x squared plus c cubed x cubed plus ... And what we want to do now, we want to talk about what it means, do arithmetic with our fractions. We want to be able to add and subtract our fractions here. So if we say let a be a generating function of an arbitrary sequence. Let a be a generating function of an arbitrary arbitrary sequence and B be a generating function of a sequence that has a multiplicative inverse. Okay, let A be a generating function of an arbitrary sequence and B be a generating function of a sequence that has a multiplicative inverse. So we would write the product of that. We can write this. This has meaning. B has a multiplicative inverse. So this has meaning. And we know from our theorems that B has to have a non-zero constant term, right? And we don't know about A. So what we want to do, let me think where I'm going right now. But what we can't do, we can't write B over A if A doesn't have a multiplicative inverse. Okay, so not allowed if A doesn't have a multiplicative inverse. Okay, so we can't write 1 over x because x doesn't have a multiplicative inverse. So this is not allowed. Not allowed. Okay, let's see where I'm sitting on time. Okay, so I want to get to I'm running out of time. Okay, so I want to look at let A also have a multiplicative inverse, and let excuse me, how do I say this? Let's write this. Okay, AB, let AB have a multiplicative inverse. The product AB have a multiplicative inverse. Then we can we know that if we multiply it by 1 over AB, we get that's equal to 1, right? And we also know that if I say, for instance, I want to multiply it this, view it from a different way. 1 over A, the multiplicative inverse A times the multiplicative inverse of B. We're not sure that's the same as the multiplicative inverse of A times B. Let's see what we get when we do this. And we can do commutativity and then associativity. So that's equal to 1 over A times A times 1 over B times B, and that's just equal to 1 times 1, which is equal to 1. So what we've proven is that this is the multiplicative inverse of AB, and part of ring theory or commutative ring theory is that multiplicative inverses are unique. So from ring theory we know that that has to be equal to 1 over AB. Let's see what we got on time. So I run out of time, and I'll pick this up next time. Thanks.